Hi, in this video, we want to take a look at confirmatory multidimensional scaling. Okay, so multidimensional scaling is where I have higher dimensions of data, and what I want to do, I want to reduce the number of dimensions, but I want to preserve the distances between the data points. Okay, so let's say I have 50 dimension data going on, and I have a distance between every single possible pair of points. All right, what I want to do, I want to reduce this down to a two-dimensional space so that I can understand it as a human being better. Okay, well, a knee-jerk response from a lot of people in the data community would be do principal component analysis, or do non-negative matrix factorization, do stochastic neighbor embedding. Those would all be reasonable choices. Now, the difference here is that we are working to preserve the distances between our data points or variables, depending on how we're approaching this. So if I do principal component analysis, what I'm doing, I'm projecting everything onto the best approximating lower dimension space. All right, that works very well, but that's not exactly the geometry we want going on in this situation. In this situation, we want to preserve distances between observations. And so we'll use multi-dimensional scaling for this. Now, this example is modified from the Springer book, Modern Psychometrics with R by Mayer. And here is the GitHub page. And we use the MPsycho-R package quite a bit in R. Okay, so what we're going to do, we're going to go through and we're going to take the OCP data set. Now, this data set is a collection of correlations between items, and we don't actually have the raw data, we have the correlations. Then we have 3 additional vectors on there. So we have a faucet for each one, a Z1 and Z2. Z1 and Z2 are the covariates that we will use for constraints in this example. So here in this example, what we're doing is we're taking the correlations between the items on the survey or on the questionnaire or on the test, whatever it is, and then we want to use that to do our multidimensional scaling. So I'm not using the actual raw data, I'm using the correlations that I get from my data. Okay, so I go ahead and just slap on row names onto it just to make things a little bit easier for down the road. So what I've got in this original data set is a correlation matrix, then categorical variable, then 2 vectors that are covariates. Well, the normal way that R handles correlation matrices, is that each row and each column have names, and the names correspond, and it's a square matrix and it's a symmetric matrix also. And so just to get things to work a little bit more similar in R than in the way that R is expecting it, I go ahead and just slap on row names. All right, so now when I look at this, it's a correlation matrix. So I need to visualize. I need some kind of intuition about what's going on. So what I'm going to do, I'm going to go ahead and use the correlation plot. So I will use core plots in the core plot package. I always like to put in ellipses because the ellipses, if it's positive correlation, go in a positive direction, negative goes in a negative correlation. I'm not going to print anything on the diagonal, and I'm going to order things by H cluster. I strongly recommend that you order things by clustering because it makes it much easier to read. So let's go ahead and take a look. All right, now we can see the names are going to be like I1, I2. That's for item 1, item 2 of the original questions. Remember, I don't have the actual data, I have their correlations. Now, if we look down the diagonal here, we can see that we kind of like have these blocks going on. These blocks of correlated items are coming together. And this is why I like to use the H cluster method of ordering, is that it's easier for me to see. Now, if I zoom in and I can see more precisely what the item labels are, I can do a deeper analysis. But here, at least I have a feel for what's going on. I can see that here I have a block of correlations, And when I look at the corresponding blocks between them, I can see we have negative correlations. So, this gives me some insight into what's going on. All right, so now what I'm going to do, I'm going to fit a multidimensional scaling model without using any constraints, without using any covariates. All right, so here I'm just going to use the multidimensional scaling function from SmackOff. All right, and so, something I forgot to say. So when I do the multidimensional scaling, we want to pass dissimilarities, not similarities. So correlation measures the similarity between things, and dissimilarities measures the dissimilarities between things. So what I really need is something more similar to a distance matrix. Now, this may or may not be an actual distance matrix, but for our purpose, it'll be close enough. So what we want to do in the SmackOff package, I want sim to dis to convert the correlations into a dissimilarity matrix. And so I've got the dissimilarity matrix here. And here we're saying we have ordinal data. Okay, and so my stress value is 0.23. Now this is no constraints, no restrictions. This is really the best that I can expect to do off of any other model that I build, because I'm letting the data speak 100% for itself. Now, if I have subject matter knowledge where I know that constraints are appropriate, that constraints are actually needed for the true actual model, then I'm going to fit it and I'm going to compare it to that. 0.23 is going to be the best I can do. But remember, there's always a difference between my data and the true population. What's going on here, when I let my data do 100% of the speaking, I can overfit. And so this might be the model might be fitting the data too much compared to the actual true population. By having constraints, I can control and make sure that things are the way they actually should be. All right, 30 iterations, something good to know about. Keep that in your mind. Now let's go ahead and look at the plots of all of them. And here, I'm not going to get too deep into it, but here is the two-dimensional lower dimension representation of the data. And we see this and this looks very circular, but I have some points kind of like floating around in the middle. Here's a residual plot. So this is going to be the normalized distances and the configuration distances. So we have a feel for like how much of a change it is. The shepherd plots. And since it's a type ordinal, we can see that it's a stair-step model. Here is the stress plot. So this shows me which items have the biggest discrepancy between their original distance and their transform distance. So remember, my goal is to take the higher dimensional distances, take my data into lower dimensions, and keep the distances between points to be exactly the same. That's my goal. Now I can see here which ones was I achieved for the best and which ones were the worst. So item 23, this modeling structure worked very well for. Item 48, not so much. All right, so the bubble plot did not plot right. Yeah. So all right, so the worse the performance of the model, the bigger the bubbles. For some reason that did not plot. Why didn't it plot? I don't have any constraints on it. All right, well, oh well. Oh, something I need to say about stress. Remember, stress here always adds up to 100%. So this tells me relative, items relative to each other, which ones are worse, which ones are better. If I have a very good fitting model, this item 48 may be very good, but on this scale, it looks bad. But if in reality, 48, it actually has good, a good small amount of stress overall, because remember, things are proportional to each other. Everything adds up to 100%. I can't tell that. This just tells me relative to each other. And histogram of the dissimilarities. And let's go ahead and plot things so that I can use that faucet information that we have. And remember, this is unrestricted. So I can see like 48 and 10, 46 and 44 are about openness to change. And then self-enhancement, 35, 36, 40. And let's see, conservation is like 52. These are the ones that are moving, that are closer to the center, away from that circle aspect. So those are the ones I'm kind of watching out for. All right, so now let's go ahead and build some models with constraints. All right, so what I'm going to do, I'm going to take the constraint covariates, and I'm just going to call that Z. And unique Z is here. All right, so we see that when we have NA, that means there are no constraints whatsoever. And when I have numbers, we have constraints. So what's going on is that I have 4 different locations in the subspace that I'm putting things in for constraining. All right, so here I'm going to do a Smakoff constraint function. And the big difference here is that I need to say, all right, these are the constraining aspects. Here is ordinal. And so this is the original data. The original data is ordinal. The constraint is ordinal here. We can see that we have stress value of 0.32. And let's look at the plot. All right, so now I notice that all the reds are together. I notice that the teals are together. The purples are in a cloud, and the other I can't tell what color that is also here. All right, so we can see that by constraining in an ordinal manner, it moved things around so that they kind of like form clouds together. Now, the black ones, by the way that I coded this, are the ones that have no constraints whatsoever. They land wherever they land. Now let's do this with interval constraints. And so the big change here is that I put constraint type equal to interval, and let's see what happens. Wow, look at that. Look at the difference. So first and foremost, all the unconstrained ones are just wherever they want to be. Now, these 4 are grouping together, like all the ones that are in this group are stacked on top of each other. All the ones in this group are stacked on top of each other. All the ones in this group are stacked on top of each other, and these are stacked on top of each other. This is the interval constraints. Now, something about this package is that this treats interval as y equals mx plus b. Okay, so keep that in your mind when you're making a choice. Interval actually has more flexibility in the ratio. Ratio will be y equals mx. So here, interval means that we have a straight line with any intercept. Ratio has a straight line passing through the origin. And so now let's do ratio for my constraint type. I can look and see, I get something very similar. All right, so there really wasn't much of a difference visually going from interval to ratio. Ratio has more restrictions. All right, now the next option we have is to change up this. So previously we were doing like a linear, like a matrix multiplication version of the constraints. Now I want to constrain everything onto a circle or a sphere. Okay, when I do this, I'm going to use the Smakoff sphere function. I'm going to pass my dissimilarity object. Now, the greater the penalty, the more I'm going to force the points onto the circle. If the penalty is small, it's just going to move the points a little bit to a circle. If the penalty is big, it's going to force it on, like right on that circle, super tight. And here, this is saying that the original data set, not the constraints, the data is ordinal. So now let's take a look. Now notice that it's 0.26 for my stress. And let's look at this. And here we can see where each of the points land on the circle. And so something that's jumping out at me is that we see all these guys are grouping together, all of these are grouping together, but there's a couple that just aren't with their groups. Like item 10 just doesn't want to be with this group. 46 isn't with this group. 48 is kind of like deviating away from its group also. So it might be that these are mislabeled in terms of their faucet. That might be that there's something weird going on with data recording. I don't know. Maybe this is just how it is. We would have to investigate deeper. Now let's compare our models. So with no constraints, my stress was 0.23. Ordinal was 0.32. Ratio, let's see. Oh, sorry, ordinal is 0.32. Interval is 0.48. Ratio is 0.48. Visually they were pretty much the same. And spherical is 0.26. Okay, so this makes me feel like of these constraints, spherical matches the data the best. And when I looked at the original data, it's like, yeah, that looked like it's on a circle. So for a little bit of increase in stress, I have a much more complete model structure. So I'm liking the spherical constraints for this data set. Well, I hope you enjoyed the video. Take care and goodbye.